Welcome back. Today we are going to discuss about the problems related to the undamped free vibration. In the last session, we have discussed the one stepped bar problem. Today also we are going to discuss the stepped bar problem with a numerical values. So the problem is like this. So here the problem is given in the it is stated that evaluate the eigenvectors and eigenvalues for the stepped bar as shown in figure, and provided that he given some of the data, take E is equal 200 gigapascal. Young's modulus for the entire stepped bar is given 200 gigapascal, and specific weight it is given that is called the specific weight is given that 7850 Newton per meter cube for entire stepped bar, and is going to ask that again draw mode shapes, and also given that the take A1 is equal 400 meters square, means that there are the two different cross section. First cross section term as A1 and second one is a A2, and where A1 is given in the problem 400 meters square square, and A2 is given that it is a 200 square. So these are the data that is given in the problem. Okay, so this is the data that is given in the problem. So let will try to solve this problem. Let will try to solve this problem. So here in the finite element analysis, the steps are: first we have to be select the domain that is called this entire step ball, and we need to discretize this domain into the subdomains. So here we are going to be discretize this into the two different elements, means that we are dividing the two subdomains, that is called area 1 as a one element and area 2 as a second element. So area 1 term as a first element and area 2 is term as a second element. So here the total number of element in this discretization process, let us assume that is only two elements. Why we are going to restrict it to the two means, so to simplify the process manually, so we are going to be identify that there are the two different cross section. That's why we discretize it to the two different elements. So first element has the area A1, and also it has a Young's modulus that is called E, and also it has a length 200 Similarly, A2 is also the second element having the area A2, and it is also having the density, and it is also having the length that is called 100 So using this data, let us try to find the unknown values. So in the problem, the density is given that 7850 in terms of Newton cube. Newton per meter cube is given, and let us convert this into the kg per meter cube. So if we convert into the kg per meter cube, then you have to be divide the 9.81. So if you are dividing with the 9.81, then you will get the density is equal to 800.2 kg per meter cube. Now let us try to find out the what is the global stiffness matrix for this stepped bar as well as global mass matrix for this stepped bar to solve the undamped free vibration problem. So the undamped free vibration problem, it is necessary to find out the what is the global stiffness matrix for the given problem as well as global mass matrix for the given problem. So to find out the global stiffness matrix, first we have to be find out the first element stiffness matrix, second element stiffness matrix, that is called K superposition 1 and K superposition 2. So once you get the K superposition 1 and K superposition 2, then you should combine the K1, K2 to get the global stiffness matrix. In the same way, for the global mass matrix also, you need to be find out the first element mass matrix as well as second element mass matrix. Once you get the mass M1 and M2, then you should be combine the M1 and M2 to get the global stiffness matrix. Let us try to solve the global stiffness matrix for the stepped bar as well as global mass matrix for the stepped bar. So in this one, first element, the K superposition one, that is called element is belongs to the A1 area. So in this one, the stiffness matrix is equal to the for stepped bar element AE by L into 1. This is not minus 1, this is 1 minus 1 minus 1 1. So this is the formula for the any element that belongs to the bar. So for bar element, the step bar formula is equal to AE by L into 1 minus 1 minus 1 1. So here the A is given that for first element it is equal to 400 mm. So convert into the meter square. So therefore 400 into 10 power minus 6. And E is given that 200 gigapascal. So convert into the Newton per mm square, that is equal 200 into 10 power 9, and divided by the length of an element. It is given in terms of the mm, so convert into the meters, that is called 0.2. So into AE by L into 1, this is 1 minus 1 minus 1 1. So simplify this K1, you'll get the 10 power 8 4 minus 4 minus 4 4. So this is a simplified matrix of the first element, that is called K superposition 1. Similarly for K superposition 2 also, because for second element the area 2 is given that 200 mm and the length is given that 100 mm, as well as the density, then we know that Young's modulus is equal to the 200 gigapascal. So every term is known. So AE by L into 1 minus 1 minus 1 1. So that will give the value of the 10 power 8 4 minus 4 minus 4 4. So this is the value for the second stiffness matrix. So this is a value for the second element stiffness matrix. So once you get the K1 K2, then you have to be combine the entire K1 and K2 to get the global stiffness matrix. Once you do the assembling method and forming the global stiffness matrix, here straight away I written here because we already discussed in the last previous units elaborately how to find the or how to get the global stiffness matrix once you know the each and every individual element stiffness matrix. So we discussed elaborately in the last previous 4 units, and the same way we are going to be find out the global stiffness matrix here. The global stiffness matrix we got here 10 power 8 into this 3 by 3 matrix, and that is called 4 minus 4 0 minus 4 8 minus 4 0 minus 4 4. So this is the global stiffness matrix. So once you found the global stiffness matrix, let us focus on to the global mass matrix, because to find out the eigenvalues and eigenvectors, it is very important to find the what is the global stiffness matrix as well as a global mass matrix. So now we got the global stiffness matrix, and let us focus on the global mass matrix. Here we are going to be consider the consistent mass matrix approach. In the consistent mass matrix approach, for a bar element, the consistent mass matrix formula is given that rho into A into L by 6 into 2 1 1 2. So this is the bar element consistent mass matrix formula. Using this consistent mass matrix formula, let us find the what is the consistent mass matrix for the first element and similarly for second element. Here I've calculated that the consistent mass matrix for the element 1, that is called M1, is given that rho is given that 800.2 into area is 400 into 10 power minus 6 into length is for first element 0.2, and that will give that into 2112. After simplifying, you will get that, and 10 power minus 3 into 21.54, 10.4 and 10.07, 21.31. So this is a consistent mass matrix for the first element. Similarly, for second element also you have to calculate the consistent mass matrix for the second element, that is called M2. So that formula is again rho A L by 6 into 2112. So using this formula, it is possible to find out. Then after simplifying, you will get the consistent mass matrix for the second element is equal to 10 to the power of minus 3, 5.34, 2.67, 2.67, 5.34. So this is the consistent mass matrix for first element and second element. Once you get the consistent mass matrix for the first element and second element, then you have to be combine this M1, M2 similar to the global stiffness matrix approach. So once you combine this M1 and M2, you will get the global mass matrix. The global mass matrix we obtained here 10 power minus 3 into this 3 by 3 matrix, that is equal to 21.34, 10.670 and 10.67, 26.68, 2.67, 2.67, 5.34. So once you got the global mass matrix as well as global stiffness matrix, now let us apply the governing equation for the free vibration undamped problems. In this problem is belongs to the free vibration problem because there is no external force. If you see the problem and clearly say that there is no force is acting on a member, so means that this problem is belongs to the free vibration problem and there is no damping, so therefore we can say it is undamped free vibration problem. So if undamped free vibration problem is given in the problem, the governing equation would be it is equal to the k minus lambda m into u is equal to 0. So this is a modified governing equation for the undamped free vibration problems, where k is equal to global stiffness matrix, and here lambda is nothing but it is equal to the omega square. So lambda suffix I, this is given that omega suffix I whole square means that the natural frequency whole square into m into that is called u displacement matrix, that is must be equal to 0. Because why? Because there is no external force. If the external forces are there, this matrix, this 0 becomes the force matrix. Here the force matrix is 0, so that's why we use that it is equal to the 0. But in some other cases, some problems may be the forced vibration. So if the forced vibration problems are given, so therefore instead of 0, you will get the force matrix here. That is the only difference between the free vibration problems as well as forced vibration problem approach. In the free vibration approach, the entire force acting on a member or given problem will be equal to the 0 matrix. But whereas in the forced vibration, the forces are existing in terms of the matrix. We know that in the last 4 units, how to find the force matrix for the bar as well as beam as well as the truss. So in the same way, if the force vibrations are there, this equation becomes that it is equal this matrix of k minus lambda m into u is equal the force matrix. So that is the matrix we'll get for the force of vibration. But now this given problem is only free vibration problem. That's why the k minus lambda m into u is equal to the 0. So here the k is equal to global stiffness matrix, and that is after apply here 10 power 8 into 4 minus 4 0 minus 4 8 minus 4 0 minus 4 4 minus of lambda I into global mass matrix is 10 power minus 3 into 21.34 10.670 10.67 26.68 2.670 2.67 5.34. This is a global mass, and that into the displacement matrix. Here there are the two different cross sections are there, so you'll get the 3 nodal point, nodal point 1, nodal point 2, nodal point 3. So let us assume that at nodal point 1 the displacement is equal to u1, nodal point 2 the displacement is equal to u2, nodal point 3 displacement is equal to u3. So therefore the displacement matrix is always, it is a column matrix, that is called u1 u2 u3. So that is applied here u1 u2 u3, and that must be equal to 0 because it is a free vibration. So here the boundary conditions you should apply before solving this equation, because at nodal point 1 it is given in the problem, and by seeing itself we can say that it is a fixed at nodal point 1. So if it is a fixed at nodal point 1 means that the nodal point 1 is arrested. So there is no displacement at nodal point 1. So therefore u1 must be equal to 0. So if u1 is 0, now let us apply the elimination process to reduce the complexity of the problem. So if you apply the elimination process here, you should eliminate the first row and first column here. And similarly, in the global stiffness matrix also, you should eliminate the first row and first column. So therefore, the K is reduced to 2 by 2 minus lambda into M is reduced to 2 by 2, and that must be equal to the 0. But because here U2, U3 is existing, then you have to be sent to this other side. It becomes the 0 into something become the 0. So therefore, the data of K minus lambda M must be equal to 0. So this is a approach to find the lambda values, because we converted this free vibration problem into the eigenvalues and eigenvector problems. So from this data of K minus lambda M, data of is equal to 0. So from this, it is possible to find out the what is the lambda values here. So here 2 by 2 minus of lambda 2 by 2. Okay, so once you do the subtraction from the K minus of lambda M, you will get the only 2 by 2 matrix. So the 2 by 2 matrix will go into obtain here. So the data of this 2 by 2 matrix must be equal to 0. So that is nothing but this. Let us say this is A and B and C and D. So the data is equal to AD minus BC. So if you apply that formula, therefore you'll get the below one. And from this one, it is possible to find out the lambda values is equal to the lambda 1 as well as the lambda 2. So the lambda 1 will get from the equation, it is equal to the 1.16 into 10 power 11, and a lambda 2 is equal to 1.019 into 10 power 10. Or otherwise, we can write this as a 0.102 into 10 power 11. So these are the lambda values, lambda 1 and lambda 2. This is called as eigenvalues for the given problem. So from this eigenvalues, the lambda 1, we know that it is must be equal to the natural frequency square, omega n square. So therefore, it is possible to find out the what is the natural frequency at lambda 1 and what is the natural frequency at the lambda 2. So at lambda 1, the natural frequency can be written as under root of lambda 1. Okay, so under root of lambda 1 is nothing but this is a under root of 1.16 into 10 power 11. So therefore, omega n, that is can be written as 340. 340,587.7273. So this is the natural frequency at lambda 1. Similarly, at this lambda 1, it is possible to find out the what is the cycles per second, that is called F1. That can be written as it is equal to the natural frequency divided by 2 times of pi, and that can be possible to find out 54283.714 Hz. This is the cycles per second. So at lambda 1, it is possible to find out the natural frequency as well as the F1. Similarly, at lambda 2, it is possible to find out the what is the natural frequency as well as F2 here. So we obtain that natural frequency is equal to lambda 2 is equal to 100,995.0494, and similarly F2 is equal to 16082.014 Hz. So these are the natural frequencies as well as the cycles per seconds at lambda 1 and lambda 2 values. Now, so once you find out the eigenvalues, the next step is we should find out the what is the eigenvector. So to find out the eigenvectors, anyhow u1 is going to be 0. So because we use the elimination process to reduce the complexity of the problem, so the eigenvector that is equal, this is called at lambda 1, we should find out what is a u1, u2, u3, and similarly at lambda 2, what is a u1, u2, u3, that is called eigenvector. So this is called as an eigenvector. So we need to be find out what is the eigenvector at lambda 1, and similarly what is the eigenvector at lambda 2. Anyhow, at lambda 1, at lambda 2, the u1 is going to be 0, and only thing is we need to be find out what is the value of u2 and u3 for lambda 1 and lambda 2. Okay, so let us try to solve the eigenvector. So to find out the eigenvectors, we are going to be use that the k minus lambda 1 into m into u1 is equal to 0. So this is the equation to find out the eigenvectors given lambda 1. So the u1 must be equal to the u2 and u3. So here, this is the eigenvector that is equal matrix of u1 will be equal to the it is a u2 and u3. So you need to be find out what is a u2 and u3 at lambda 1. So for this one, it is possible to write that k minus lambda 1 m. So where k is equal to 2 by 2 matrix and m is equal to 2 by 2 matrix. Why? Because here we reduced that the 3 by 3 into the 2 by 2 once you apply the boundary condition. So therefore, the k is reduced like this as well as m is reduced 2 by 2. So this k and m we are going to be used to find out the what is a u2 and u3 values. So substitute here k 2 by 2 matrix minus of lambda 1 we got in the last slide into mass 2 by 2. You will get the this matrix in terms of the 2 by 2 into u2 u3 that must be equal to 0. That must be equal to 0. So therefore, and once you subtract the k minus lambda 1 m, then you'll get the matrix range as a 2 by 2. That matrix range would be the 22.95, 7.097, 7.097, 2.194. This is the value for the k minus lambda 1 m matrix, and into the displacement matrix is equal to u2 u3, and that must be equal to 0. See here, this is a 2 by 2 into 2 by 1, and there is a possible to get the two equation. The first equation, first row into the say column is equal to 0, and second row into the column will be equal to 0. You will get the two equation, and u2 u3 are the two unknowns. So therefore it is possible to find out the what is a u2 and u3. So therefore it is possible to find out the u2 and u3 from this equation. The u2 is, if you say that u2 and u3 can be right in terms of the u2, that is equal minus 3.23 into u2. So this is called as a eigenvector at lambda 1, and here put down the transpose means it is always column matrix. So for getting the normalizing, okay, so for normalizing, so therefore the normalizing, the formula can be write as u transpose, that is called u1 transpose into mass matrix into the u1 must be equal to 0, or otherwise you can use that u1 transpose into k into u1 must be equal to the 1. So this is a normalization. So from this it is possible to find out the what is the value of u2, or you can straight away directly find out the u2 and u3 from this one, or otherwise you can use the normalization process. U transpose into m into u is must be equal to 0. So in this way it is possible to u transpose equal to u2 minus 3.23 u2, and u is equal, this is a column into m matrix, that is equal m matrix is equal 26.68, 2.67, 2.67, 5.34 into 10 power minus 3 into u matrix, that is equal, it is a column matrix u2 minus 3.23 into u2, that must be equal to 1. So from this one it is only unknown is called u2. So therefore it is possible to find out the u2, that is called, we got this 3.918. So once you get the u2, so it is possible to find out the u1. So that is get that once you get the u2, therefore it is possible to find out the u3, that is called minus 12.655. So therefore the eigenvector would be 3.918 minus 12.655 to the power of transpose, always because it is a column matrix. In the same approach, so we are going to use the same approach to find out the eigenvector at lambda 2. So the eigenvector for lambda 2 is equal to u2 u3. So in the same way, k is equal to 2 by 2 matrix into, sorry, k is equal to 2 by 2 matrix minus of, and lambda 2 into mass matrix 2 by 2. And if you do this one subtraction of k minus lambda to m, you will get the 2 by 2 matrix into u2 u3 is equal to 0. So at this one also you are going to be find out what is the eigenvector at lambda 2. So we'll get the eigenvector at lambda 2, that is equal to the u2 is equal to 4.91 and u3 is equal to 6.07. So this is the eigenvector at lambda 2, that is equal to 4.91, 6.07 to the power of transpose. So these are the eigenvector and eigenvalues problem. So in this way, it is very easy to find out the eigenvalues, eigenvectors once you know the eigenvectors. So the next one is it is very, very important to draw the mode shapes. So here the mode shapes is nothing but at nodal point 1 the displacement is 0 at lambda 1. So similarly at lambda 2 also we should be find out. Okay, so here the mode shapes can be find out here. For let us draw the mode shape for the 4.91 6.07. Okay, so means that this is a displacement at nodal point 2 and this is a displacement at nodal point 3. So the mode shape function at the nodal point 1 is equal to 0 and nodal point 2 is after 200 mm, it is a 4.91 and at nodal point 3 it is equal to 6.07. So this is a way to find the mode shapes for the eigenvector u2. Similarly, the mode shapes can be find out for the eigenvector u1. So at lambda 1, you will get the eigenvectors that is called u2 and u3. Anyhow, u1 is 0 and u2 will get that after 200 is equal to 3.92. But at nodal point 3, we got the value of minus 12.66. So that is down, under, and like this. I have to draw this one. So this is a way to find the or way to draw the mode shapes for the given lambda 1 and lambda 2 using the eigenvector u2 and the u1. Thank you.